Hi, everybody. For this online session today, I have three examples I want to go over with you that students asked me to answer. The first is an impulse question, which is coming out of one of the Module 1 formative assessments. I have a 2D conservation momentum problem. And actually, now that I think of it, that's my last example. I also have a 1D, because 1D is usually easier, conservation momentum problem. And these two problems are coming out of assignment questions and some of the examples from Module 2. I know that some of you aren't in Module 2 yet, but you're going to be there soon, and these are some of the questions that come up a lot, so I want to get ahead of them so you get a chance to get a little help with them before you see them in the assignments. So the first question is a question that's currently in one of the formative assessments for Module 1, but it's actually an old diploma exam question. It comes up a lot. A lot of teachers use this question because it's a really good one. It tests your understanding of Newton's laws as well as conservation. So it's a great question. So we have two carts. Cart 1 is 500 grams and cart 2 is 250 grams. So cart 1 is heavier than cart 2. And they collide. And the question asks, in which of the following diagrams is the magnitude and direction of the impulse experienced by each cart? So we've got four possible diagrams, and we want to know which one does the blue arrow represent the impulse experienced by cart 1, and the red arrow represent the impulse experienced by cart 2. So the impulse experienced by each cart is F delta T. So for cart 1, this is F1 delta T1, and for cart 2 experiences F2 delta T2. But I think we can agree that both carts experience the collision at the same time. Like the collision doesn't take more time for one cart than the other. So I think it makes sense that delta T1 has to equal delta T2. And so I'm actually going to take the little 1 and the little 2 off of that because it's just delta T. Now, there's a law from Physics 20 that you might remember that has to do with forces. Newton came up with three laws, and for Newton's third law, we know that the magnitude of the forces has to be the same. Newton's third law says that for every force imparted, an equal and opposite force is experienced. Or in other words, cart 1 pushes on cart 2, and cart 2 pushes back with the same amount of force on cart 1. So we know that the magnitude of F1 has to equal the magnitude of F2. So because delta T is the same and the magnitude of our forces are the same, the magnitude of the impulses, F1 delta T and F2 delta T, also have to be equal. So we're looking for an answer where the arrows are equal in length. That crosses out that one and that one. And we're looking for the one which is the force experienced by the cart, not the force that the cart is doing. So cart 1 is pushing this way for sure, but cart 1 is experiencing a force to the left. Cart 2 is definitely pushing this way. That's what's causing this force that cart 1 is experiencing. But cart 2 is experiencing a force from cart 1 to the right. So C is the only possible answer because the arrows are the same and it describes the forces that the objects are experiencing. So this question comes up a lot on tests. I think every physics teacher uses this question because it's a great way to test your understanding of impulse, momentum, and Newton's laws. For this next example, we're going to be doing one-dimensional conservation of momentum. Two-dimensional is coming up. Two-dimensional is harder than one-dimensional. When I say one-dimensional, I mean everything happens along the same line. So it could be like a west-east direction or a right-left or a north-south. Everything happens along the same axis. The law of conservation of momentum says that the total momentum before And by before, I mean if before some event. It could be a collision or an explosion or some interaction between more than one object. The total momentum before is equal to the total momentum after. Or writing this in math language, we would write sum of the momentum before equals sum of the momentum after. You might remember conservation of energy back from physics 20, or maybe in your chemistry class where you talked about conservation of mass, where the total energy or the total mass before and after an event, like a chemical reaction or like some object falling is common in physics 20, remains the same. The problem with momentum that makes it different from some of the conservation laws you've seen before is momentum is a vector. And so when I say sum of the momenta, I don't mean add them all up nicely. I mean you have to do a vector addition, which makes things just a little bit harder. So here's an example. And I've chosen one of the harder questions because I've already got a ton of easier examples in the lesson notes. I want to show you one that's just a little bit more tricky, so that way you're ready for it when you see it in the assignment. You've got a car traveling at 20 meters per second north collides with a truck traveling at 35 meters per second south. They stick together and travel as a unit after the collision. If the truck has 4 times the mass of the car, what is the combined velocity after the collision? This is an example of a hit and stick collision. In a hit and stick collision, the objects come together, get stuck, and travel as one object. In other words, you have 2 objects before and 1 object after. So writing down the law of conservation of momentum, we have sum of the p before equals sum of the p after. We have 2 objects before, so P1 plus P2. And we have only the 1 object after because they stick together, so that's just equal to P after. And I'm going to write out the momentum in terms of its mass and velocity. So we have m1, v1. And notice that v is the vector here. Mass is a scalar, so we don't have to worry about its direction. And then we have plus m2, v2 equals, and P after has the combined mass. So it's m1 plus m2. And again, because mass is a scalar, we don't have to worry about the addition of masses. We can just add them together like using normal addition rules. And here's our v after, which is also a vector. Now, if we look at what we're given, we have 20 meters per second to the north for v1. And so that's plus 20 because north is a positive direction. And we have 35 meters per second to the south, which means we have 35 meters per second for the second velocity, but it's negative because south is a negative direction. And we're interested in finding our v after. But that feels like all we know. How can we solve this if we're missing some of our knowns? And that's the thing with any question in physics. You can only solve if you have only one unknown in a question. So we have to add a little bit more information in order to solve for our unknown. And that comes from the fact that the truck has 4 times the mass of the car. Or m truck, which is m2, equals 4 times m1. And so we can put that in the place of m2 for m1 for m1. And I'm just going to write this out again with our knowns substituted in. So m1 times 20 is 20 m1. And then I've got minus 35, so I'm just going to go ahead and subtract 35 times 4 times m1 equals 4m1 plus m1 is 5m1 times v after. Now, you might still be thinking to yourself, well, I still have two unknowns in this question. I can't solve a question if it has two unknowns. But if you have the same thing in every term on both sides of the equation, you can divide the whole thing by that thing. So in this case, m1 appears in every term of this equation. And I can divide the whole equation by m1, which cancels m1. So that's very convenient. I never needed to know m1 in the first place. So I have 20 minus 4 times 35 is 140 equals 5 V after, which is minus 120 equals 5 V after, or V after equals minus 120 over 5, which is minus 24 meters per second. Now for Physics 30, I would like you to not write your answers as negatives, write them as directions. So in this case, we have a question that's going from the north to the south, so a negative direction means south. So we have 24 meters per second to the south. And then we'll write out in a sentence our answer, the combined velocity is 24 meters per second to the south. This next example is a two-dimensional conservation of momentum example, which means that the motion happens in two dimensions. We have a y-axis and an x-axis. So it might be north-south, or it might be up-down, it might be left-right, it could be east-west. It's the different kinds of directions we have vary. For momentum, we'll mostly use north, south, east, and west, where north is a positive direction, south is a negative direction, east is a positive direction, and west is a negative direction. And then north, south are considered to be y directions, and west, east are considered to be x directions. So in this problem, we have two objects colliding and combining together. So it's still a hit and stick collision, just like the last example. It's just now we're working in two dimensions. So for example, we have a 3 kilogram mass traveling at 10 meters per second, 15 degrees west of north. So object 1, here's my before. We have m1 equals 3 kilograms. And V1 is 10 meters per second at 15 degrees west of north. I could draw this 10 meters per second. We know it's in the northwest direction, so I'm going to draw my 10 meter per second arrow. And then it's a bit of a question of, where do I put the 15 degrees? Do I put it here or do I put it here? When it says west of north, you always look at the second direction in the of statement and you put the angle next to that direction. So we would put our 15 degrees next to the north-south line. And that's the right place to put this direction. Then we have a y component. We're going to call that Vy, and an x component, which I'll call Vx. And just thinking about SOHCAHTOA, you can see that the 15 is opposite from Vx, so it's the opposite, which means that x takes the sign. And the 15 is adjacent to the Vy, or the a in ka, which means y takes the c. So when we're breaking our 10 meters per second up into its x and y components, we're going to use sine for x and cos for y. But I don't want you to have to reason through this every time and draw a triangle because it takes a lot of time to think your way through it. So here's the trick I have for you to get through vector components quickly. When I give you an of statement like west of north or south of east, it's always going to be sine first, cos second, sine of cos, which means our west, which is x, takes the sign, and I'm going to make that a negative sign because west is a negative direction, and our y component, which is cos, is north, and that's positive because north is a positive direction. So I can break my v1 apart into its two vector components. v1x equals 10 sine 15, and I'll put a negative on that because west is a negative direction. And v1y equals 10 cos 15. Our second mass is m2, and that's 1.7 kilograms. And v2 is 12 meters per second at an angle of 30 degrees north of east. If I was to draw this out, I would draw a vector in the northeast direction, and then the 30 degrees goes next to the second direction, which is east in this case. So I would put it here next to the east-west axis. But we can go back and use my trick to figure out who gets the sine and who gets the cos more easily, just by writing sine of cos above our directions. North is positive, so it's positive sine, and north is a y direction. And east is also positive, and it's a x direction. So that gives us that our y component uses sine, and our x component uses cos. So our components of v2 are v2x equals 12 cos 30, and v2y equals 12 sine 30. So we have the given information before the collision. After the collision, because it's hit and stick collision, the masses combine. So the mass after the collision is m1 plus m2 is 3.0 plus 1.7 kilograms is 4.7 kilograms. And the problem is asking us what is the combined velocity after the collision. So we're looking for the after. Now this is a conservation of momentum problem. So we can write down the conservation of momentum law, which is sum of the momentum before equals sum of the momentum after. Because it's a hit and stick collision, we know we have P1 plus P2 equals just one momentum after, which I'll call P after. Now, because this is a two-dimensional problem, we know that there's x components and y components in the momentum. So I'm going to break this momentum down into an x direction and a y direction. So the x direction is the east-west components, and the y direction is the north-south components. So we have P1x plus P2x equals P after x, and P1y plus P2y equals P after y. So what we want to do is we want to solve two separate problems. We want to solve the x problem using our x components, and we want to solve the y problem using our y components. And then once we've solved the x problem and the y problem separately for the x component of the momentum after and the y component of the momentum after, we combine them back into the total momentum after. So let's start. Let's start with the x direction. In the x direction, we have p1x plus p2x equals p after x. Or writing that in terms of masses and velocities, we have m1 vx1 plus m2 vx2 equals m after v after in the x direction. So then let's sub in what we know. We know mass B4 is 3 kilograms. We know the second mass is 1.7 kilograms, and we know the total mass after is 4.7. We also have the two x components of the velocities before. So we have v1x is negative 10 sine 15. This is a place where you want to be extra careful when you're doing two-dimensional conservation momentum. Don't lose track of your minus signs. The first velocity is in the west direction, which means that its component in the x direction is negative. And v2 is 12 cos 30. And the goal in the x direction is to solve for the after in the x direction, or the component of the final velocity in the x direction. Substituting our numbers in, I'm going to take the negative sign out of vx1 and put it out front. So we have 3 times 10 sine 15 plus 1.7 times 12 cos 30 equals 4.7 v after in the x direction. And you'll notice that I've left my sines and cosines as they were instead of going ahead and calculating the numbers. And that's because then you have to write all these decimal places out, and it just makes it really messy and a lot of work. It's actually neater, more compact, and it's more efficient to just leave them as trig functions and plug it all in later. So then we're going to solve for VIX. VIX equals negative 3.0 10 sine 15 plus 1.7 times 12 cos 30, all divided by 4.7. And again, I really want to point out to you this negative sign, which came from the west on the first velocity. You don't want to lose your negative signs. It's just one of those places where you can do everything right and still get the wrong answer if you lose track of your negative signs. You want to be super duper careful to retain those as you go through and make sure that you're like really making note of which one's west and which one's east and which one's south and which one's north, so you don't lose track of your negatives. After plugging this into your calculator, you do get a very long decimal number, which we are going to record here. I get 9.62471986 meters per second. And I did keep all the decimal places here because you don't want to introduce rounding error too early into your calculations. You want to keep as many decimal places as you can, so that way when you go to do the final calculation, then you can round and get the accurate answer. And since this is a positive, I'm just going to make a note that what we have is an east. If I had gotten a negative answer, I would have taken that negative and rewritten it as a west. So that's the x direction, or the x component of the final velocity. Now let's do the y direction. So we use the same steps as before. We write out the momentum equation, p1y plus p2y equals p after y. And then I rewrite this in terms of its masses and velocities. m1 v1y plus m2 v2y equals m after v after in the y direction. And fill in what we know. We know that mass 1 is 3.0 kilograms and mass 2 is 1.7. And the after mass is the two masses combined, which is 4.7. And we have the components the component in the y direction of the first one is 10 cos 15. Note that this one is positive now because the y direction is north for the first velocity, and north is a positive direction. It's just the x component that got the negative on that one because the x direction was the west. And so that is 10 cos 15. And V2y is 12 sine 30. And again, we're looking for the y component of the velocity after. So substituting that in, we have 3.0 times 10 cos 15 plus 1.7 times 12 sine 30 equals 4.7 V after in the y direction. And rearranging that for V after in the y direction equals 3.0 10 cos 15 plus 1.7 times 12 sine 30 over 4.7. And when I plug that into my calculator, I get 8.335696764 meters per second, keeping all the decimal places again, so that way I don't introduce rounding error. And since I have a positive answer, that means that I take the direction to be north. So now I found the component of the final velocity in the x direction and the component of the final velocity in the y direction. I need to combine those to get the total velocity after. So I'll just total velocity after. And since velocity is a vector, that means I need magnitude and direction. The equation for calculating the magnitude of a vector from its components is the square root of its x component squared plus its y component squared. And the equation for finding the direction, which is an angle, in the case of vectors that are two-dimensional, that angle is calculated from tan -1 y over x, y direction of x direction, or numerator direction of denominator direction if you mix up the x's and y's. So we have the magnitude of the velocity after, and you'll notice I put it in absolute value signs. Absolute value signs for a vector means magnitude or just the number part. And I'm not going to handwrite in all my decimal places because it's a lot. You can go back up in your calculator and just grab those numbers if you have one of those calculators that allows you to scroll through the numbers. But you would take your VAX and your VAY, square them and add them together. So VAX squared plus VAY squared. And I don't mind if on this step you don't have to write all the decimal places either. I know it's a lot of writing. Just writing the formula is fine as long as you have the right answer in the end. I'm okay with that. So when I take my x component, which is that one, and my y component, which is that one, I square them and add them together and then square root. I get 12.73259883 meters per second. And following significant digit rules, my original numbers all had 2 significant digits, so my final answer should have 2 significant digits too. So that's 13 meters per second. The angle, which I'll call theta, is the inverse tan, or tan -1, of the y direction over the x direction. And I usually make a note at this step what the directions are. So VAY was north and VAX was east, because that's going to allow me to write the of statement later. And when I take my x component and my y component and I substitute those in, so divide y over x, so 8.335696764 divided by 9.624719864, and then I take the tan -1 of that, I get 41 degrees. I've had some questions about how do I round angles. I don't mind if you round angles always to a whole number. There's no sig-dig rules that I know of for angles. And then for your of statement, it's always numerator direction of denominator. And if you make sure to put y on the top and x on the bottom, it's always y direction of x direction. So in this case, it's north on the top, so it's north of east. So the combined velocity after is 13 meters per second at an angle of 41 degrees north of east.